Now, in the same spirit, let us look at the continuous wavelet transform. So, we are now going to introduce a more general version of the wavelet transform. So far, we have been seeing a very specific kind of wavelet transform, what we call the dyadic discrete wavelet transform. There, the scale parameter is changed in powers of 2. The translation parameter is changed by uniform steps. The step depends on the scale. So, if you look at the Haar multi-resolution analysis, of course, the scale is changed dyadically, that means in powers of 2, and the translation is changed in steps of unity when you take the basic or the middle so called subspace V 0. And as you go towards higher subspaces in that ladder, the step size becomes smaller in powers of 2 steps. As you go lower in that ladder, the step size changes again by factors of 2, becomes bigger and bigger. Anyway, so we need to understand this from a time frequency plane perspective. So, in general, what is the continuous version of the wavelet transform? The continuous version of the wavelet transform is essentially a dot product again. It is an inner product of x t with, now this time instead of a window we have a wavelet, a translate and a dilate of a wavelet. So, we take the wavelet psi, we translate it by tau naught and we dilate it by a factor S naught. Psi is a wavelet. Now, what on earth do we mean by that? What in general is a wavelet? In fact, we shall indirectly postpone the answer to that question for a while until we complete this discussion on the continuous wavelet transform. So, what qualifies as a wavelet is a question that we need to answer. Well, we know examples of functions that qualify as wavelets. With tongue in cheek, we will say the Haar function qualifies as a wavelet. I said tongue in cheek because actually it has an infinite frequency variance. So, we have trouble there. But anyway, as I said, tongue in cheek. But we know better examples of wavelets. We know the Dobash wavelets, for example, maybe more difficult to construct, but nevertheless there for us, and we have a whole family there of Dobash wavelets. So, we have examples of wavelets, which are restricted in time and restricted in frequency. So, one thing that we very clearly understand is that the wavelet function needs to be restricted in time and restricted in frequency. It needs to be a window function in some sense, but just any old window function, that we shall take some time to answer. Anyway, so for the moment, leaving open the question of what qualifies as a general wavelet, let us come back to this inner product here. We are taking to construct a continuous wavelet transform an inner product of x t with this wavelet function dilated by S 0 and translated by tau 0. Of course, S 0 must be non-negative. So, the way to write it is S 0 belongs to R plus. This plus means that S 0 is a positive real number, excluding 0 and excluding all negative real numbers. Let us write that inner product down for ourselves. So, we are saying this. Now, again here we need to exercise a little bit of caution. You see, if we use this as it is, then we have what is called the problem of normalization. this problem of normalization did not come in the short time Fourier transform, because when we modulated and when we translated in time, the norm of the function was unchanged. But here when we dilate, then the norm changes and we need to take care of that. So, we need to normalize. And that I leave to you to prove can be done by multiplying by a factor of 1 by square root of S 0. So, if we take 1 by S 0 positive square root times psi t minus tau 0 by S 0, then it is normalized. All right. It has a norm equal to the norm of psi t. So, this has the same norm as psi t without the translation and dilation. Anyway, so let us construct this dot product. The dot product becomes integral x t psi t minus tau 0 by S 0 dt with a complex conjugate on this. Now, of course, if psi t is real, then the complex conjugate is redundant. And that is what we have been doing in all the real wavelets that we have been using, ignoring that complex conjugate. Now, let us interpret this also in the frequency domain sense. What are we doing there? Let us use Parsifal's theorem again. This is also equal then to the inner product of x cap omega with the Fourier transform of psi t minus tau naught by S naught. And let us evaluate this, the Fourier transform of t minus tau naught by S naught. Of course, normalized with this. And here again, although I did not need it inside the integral sign, I should keep the 1 by S naught to the power of half outside the integral sign. So, I must bring in the factor here for completeness. So, let us evaluate this. Now, the Fourier transform of 1 by S naught square root psi t minus tau naught by S naught can be calculated as follows. We will do it in 2 steps. We will first go from psi t to 1 by square root S or square root S naught psi t by S naught, and we will make use of the property of the Fourier transform pertaining to scaling the independent variable. So, we make use of that property first. So, it is very easy to see that the Fourier transform of 1 by S naught to the power half psi t by S naught becomes S naught to the power of half psi cap S naught omega. So, because of the normalization, the 1 by square root of S naught here and the 1 by S naught becomes square root of S naught here and S naught there. And of course, remember S naught is positive and real. So, we do not need to worry about the sign, a modulus is not required. Now, if we wish to find the Fourier transform of 1 by S naught square root psi t minus tau naught by S naught, all that we are doing is to replace t by t minus tau naught, and that amounts to multiplying in the Fourier domain by e raised to the power minus j omega tau naught. So, we will do exactly that. Therefore, we have the Fourier transform of psi t minus tau naught by S naught into 1 by S naught square root is square root of S naught psi cap S naught omega multiplied by e raised to the power minus j omega tau naught. And we put this back in the expression that we had for the continuous wavelet transform. Remember, the continuous wavelet transform is a continuous function of the translation tau naught and the scaling S naught. S naught is only positive real, tau naught is both negative and positive real. Let us emphasize that. So, let us write both of these down and let us introduce notation here. The continuous wavelet transform which we shall abbreviate by CWT, and here again it has primary and secondary arguments. So, CWT will have the secondary arguments x and psi and the primary arguments tau naught and S naught. And this reads as the continuous wavelet transform of the function x, which presumably belongs to L to R, with respect to the wavelet psi evaluated at the translation tau naught and the scale S naught. So, this quantity CWT of x with respect to psi evaluated at tau naught and S naught is either, if you wish to look at it that way, the dot product of x t with psi t minus tau naught by S naught normalized with 1 by S naught, either this or, as we have just seen using Parseval's theorem, the following. Of course, with a factor of 1 by 2 pi. So, let me keep that factor of 1 by 2 pi here. This is of course complex conjugated. So, I need to rewrite this a little bit. There is a complex conjugate here in general. I have taken care of the complex conjugate here by replacing the minus by a plus. Now, this has a very interesting interpretation, provided we recall the nature of the Fourier transform of psi from the examples that we have seen so far. You will recall that if we considered the Haar wavelet, for example, psi t was a band pass function. In fact, just to recall, let me put down the magnitude pattern of the Fourier transform of psi t in the Haar case. Recall the Haar case. It had a magnitude Fourier transform which looked something like this. It had the first null at 4 pi and subsequent nulls of side lobes at all multiples of 4 pi beyond, and the main lobe essentially was a band between 0 and 4 pi. So, it was a band pass function. By a band pass function, I mean it did not have a non-null Fourier transform at 0. As omega tends to infinity, again the Fourier transform decays towards 0. So, the Fourier transform magnitude is 0 at 0, 0 at infinity, and maximum somewhere in between. It emphasizes a band of frequencies. We saw that explicitly in the case of the Haar function. I encourage all of you to explicitly calculate the Fourier transform of the Dobash 4 wavelet, for example. It would be interesting to do. It has to be done numerically and verify that that would also have this band pass character. So, we see the trend in these so called wavelet functions. They have a band pass character, and if we allow that interpretation, then what we have written here has a beautiful meaning. It means that we are multiplying the Fourier transform of x with a band pass function scaled in the Fourier domain by the factor S naught, and we are calculating the inverse Fourier transform of the same. Of course, this factor of square root of S naught is here to normalize. Now, if you accept that psi is a band pass function, then what you are doing here is essentially to extract a region of frequencies in the Fourier transform of x, which lies around the appropriate dilate of the Fourier transform of psi, and you are calculating the inverse Fourier transform. The inverse Fourier transform, this integral after multiplication by e raised to the power j omega naught omega tau naught with respect to omega, essentially means the output after doing this work in the frequency domain. So, what we are saying in effect is the following. We are saying that in effect, if we accept that psi is a band pass function, then the interpretation is as follows. In the continuous wavelet transform, we are taking x, we are passing it through a band pass filter. Whose impulse response is essentially 1 by S naught square root psi t by S naught. Well, if you like, one should complex conjugate this, because you are doing a complex conjugation there as well. So, you complex conjugate this, and strictly you should also put a minus sign here, because this would be the inverse Fourier transform when you complex conjugate in frequency and then scale by S naught. The output is the CWT as a function of tau naught. At the scale S naught. So, at every scale there is a different filter. You have a continuum of filters indexed by S0. For every scale S0 there is a different filter. It extracts information in X cap around the center frequency appropriately scaled by S0, and the band is also scaled. Remember, when you scale the center frequency, you also scale the band. Recall all this discussion in the HAR. Now, we are doing it for a general band pass function, and that inverse Fourier transform is operated by tau naught. So, you are calculating the output at each point tau naught. This is the interpretation of the continuous wavelet transform. So, with that then we come to the end of this lecture, where what we have seen is essentially the definition and the interpretation of the short time Fourier transform and the continuous wavelet transform. Thank you.